presented by Caltech.
Good evening. Thank you for coming through the rain. I am Jean-Laurent Rosenthal, the chair of the Division of Humanities and Social Sciences. It's a pleasure and an honor to introduce the speaker for tonight's Ernest C. Watson Lecture Series, Professor Omer Tamuz. Professor Tamuz received a bachelor's degree in computer science and physics from Tel Aviv University, and then a PhD in mathematics from the Weizmann Institute in 2013. After a stint as a postdoc at MIT and Microsoft Research, he joined Caltech in 2015 and is now assistant professor of economics and mathematics. As his very brief history suggests, Omer Tamuz embodies the interdisciplinary interaction that makes Caltech scholars unique. We are not just one thing. The best of us build paths between fields and use these paths to solve important problems. Professor Tamuz enjoys traveling through the disciplines, but unlike the problems he's going to talk about tonight, his progress is entirely non-random. It is instead something quite extraordinary. Motion of confidence and relaxed intensity. Relaxed because it seems that Omer always has time for another student in his office, another hallway conversation with a colleague or graduate student. Intense because in fact those students are in his office proving theorems and discussing hard problems. Intense also because one day as we're walking to lunch, he said to me, "Did you know that the optimal random audit rule follows the golden ratio?" What could I say but raise my eyebrow in suspicion? By the time lunch was over, I was convinced, and I now visit his office every 1.6 weeks, with some randomness added. I also recalled that when he was giving his job market talk about optimal diffusion of information along a network, he spent most of the time explaining to us the ideas that the network cannot be locally too sparse or too dense, and why that was the case. Too sparse and information does not flow enough. Too dense and individuals will start to conform too much. Then as an aside, he kind of squinted and muttered, "We have to build some new math to solve this one." That leaves confident. When Omer Tamuz came, he said he wanted to do math and social science, and he was not sure we would let him do so. I told him, yes, you can. And as you will see tonight, yes, he does. Tonight, Omer will speak of the long-run behavior of random walks. Please join me in welcoming my colleague and friend, Omer Tamuz.
Hi, thank you very much. Thank you, Jean-Laurent. I want to thank the Office of Strategic Communication for helping prepare this, and thank you all for coming in this rain. Okay, so I'm going to talk about random walks, and this is a talk about math mostly. I'm going to try to keep the calculations and the numbers to a minimum. There'll be a few here and there, but if they scare you, then just tune them out and skip a minute and you won't miss anything. You can join right later. For those of you who happen to be mathematicians or experts in this field, some of the things I'm going to say are a bit loose, so forgive me for any inaccuracies. Some of the terms I made up especially for this talk, so yeah. I hope to disappoint everybody equally. Okay, so what is a random walk? There are a few different types of random walks, and we're going to start with the simplest one, which is a simple random walk on the integers. So the integers are represented by these dots. This is, say, 0, 1, 2, and then -1, -2. And we have some person or particle or something that starts, say, at 0, and we have a clock that ticks, and every tick of the clock, this person is going to move either left or right with probability 1/2. So it's very important for me that we really understand this, so I want to give a little demonstration. I have here a deck of cards. I'm not going to do a magic trick, but I am going to shuffle them, so things are random. And I'm going to need a volunteer from the audience. Who? Maybe you? Come. Random boy that I've never seen before. What's your name? Amir, okay. Stand right here. So what I'm going to do is, I shuffled the deck, and I'm going to draw cards from the deck one by one. And if it comes out black, I'll say right. And if it comes out red, I'll say left. And whenever I tell you right, left, just move one cone left or right. Got it? Okay. Okay, so let's do a random walk by a random child. Right. Left. Right. No, that was wrong. Go back. Left. Right. Left. Right. Left. Right. Left. Wow. Right. Right. Left. 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 Right. Okay, so that's how it goes. Thank you. You can go back. Okay, so the basic idea is very, very simple. We have a random process. In this case, it was drawing cards. You can imagine that I tossed a coin, or maybe I used a computer to do this. And I have some object, in this case a person, that moves right and left each time with probability 1/2. So people in math study this. Well, that's a good question why they study this. They think it's interesting. They think it's beautiful. That's usually the motivation of mathematicians. But this is actually an important model in science. So this thing could be a boy jumping left and right. It could be a particle that's being hit by other particles, which sometimes move it to the right, sometimes move it to the left. That's called Brownian motion. It could be the price of a stock that goes up and down randomly over time. So understanding what happens with this very simple model does have implications to how we understand all sorts of real physical, financial, biological, and other processes. Okay. So let's try and see what happens with this random walk. What I have on this graph here is what happens after 2 ticks. So we started out in the middle. After 1 tick, with probability 1/2 was at 1 and probability 1/2 at -1. After 2 ticks, either I came back to 0, or I went to 2 or to -2. And it turns out that with probability 1/2, I end up back where I started. And with probability 1/4, I'm at -2, and probability 1/4, I'm at 2. This is what it looks like after 20 ticks of the clock. So now you see that it's somehow spread out. There's still decent probability of being at 0, about about 17%, and then it drops off. And even though 20 ticks have passed, the probability of actually being at, say, -20 is very, very small. To be at -20 after 20 ticks, I would have had to go left every single time. Would have had to toss 20 heads one after another. That doesn't happen. That's a chance of 1 in a million, actually. Let's look at what it looks like after 100 ticks. So now the probability of being back at 0 where I started is about 10%. And then it tapers off sort of gently. And you can see that, say, around -10 and 10, most likely I'm somewhere between -10 and 10, and then it kind of drops off very quickly. The probability of being beyond 30 is, again, very, very small. It's should be about less than 1 in 10,000 or something of that order of magnitude. So even though I've taken 100 steps, I've most likely gone only about a distance 10 from where I started. And this shape is something that appears very frequently in probability and also in many physical processes. It's called a bell curve or a Gaussian or a normal distribution. And indeed, if we look at what happens at time t, after t ticks of this clock, it's going to look more and more like a perfectly smooth, beautiful bell curve. The width of this bell curve is going to be about the square root of the time. So at time 100, like we saw here, most likely I'm between -10 and 10. The width of this bell curve at time 100 is about 10. In fact, with about probability 70% or 68%, I'll be within square root t of 0 of where I started. So at time 10, I'll be between -10 and 10. At time 10,000, I'll be within the square root of 10,000, which is 100. So within 100 of where I started. At time 1 million, I'll be within 1,000 of where I started. So 1,000 is much, much less than 1 million. I've taken 1 million steps, but most likely I've not drifted off more than 1,000 locations from where I started. And in fact, so the rate at which I escape, at which I leave this place where I started, is much, much slower than if I was just walking straight. Okay? So I'm going to mention a few of the people who pioneered and made major contributions to this field. The first person I'll mention is George Polya. He's an Hungarian mathematician. He was born in 1887. He was a professor in Switzerland for a while, then he moved to Stanford in the 40s. And he asked the following question: what is the probability that the random walk will eventually return to the origin, return to where it started? So when we had the random boy do the random walk, I think right in the beginning he went right and then immediately back left and came back to where he started. Okay? But you could have imagined that just by chance he would have taken, I don't know, 3 steps to the right, and then 1 to the left, and maybe 1, and maybe eventually, maybe it's possible that he would never come back to where he started. So this is the question that Polya asked: what is the probability that the random walk on the integers never comes back to the origin? Or what is the probability that eventually it comes back to the origin? So we want to know what happens after a long, long time. Do we necessarily come back? Or do we not necessarily come back and with some probability drift off? So there are names for these things. We call a random walk recurrent if it returns to where it started with probability 1. If with 100% probability, it returns to where it started. And we're going to call it transient if this probability is less than 1. The probability is, it's never going to be a 0 chance to return to where I started. If I started here, there is a decent chance that I go right and then go back left to where I started. But maybe there is some chance that I never come back, in which case I would call the random walk transient. If I necessarily come back, it's recurrent. Now, a recurrent random walk, so a random walk that comes back, will then again come back and again, because once I've come back to where I started, I just start afresh and keep on walking again. So if before I had to come back, the second time I again have to come back, and then the third time, and so on. So a recurrent random walk will come back again and again and again. A transient random walk may come back a few times, but eventually it would leave and never come back. So Polya asked, which kind of random walk is this simple random walk on the integers? Recurrent or transient? Okay? So it's a bit of a big crowd to take, to ask you what you think, but you should ask yourself, what do you think? Do you think that this particle that's being pushed around by particles will eventually come back to where it started? Or is it going to drift off? Here's another sort of economic application. Imagine that I'm gambling at a coin toss, and when I guess correctly, I get $1, and when I guess incorrectly, I lose $1. So now I can look at my bank balance, and it goes up by 1 each time with probability 1/2. It goes down by 1 each time with probability 1/2, exactly like this random walk. And if my bank balance starts at 0, I can ask, does it necessarily always going to come back to 0? Or is it possible that it goes up and never comes back down to 0? Polya's theorem, and Polya's theorem has a few parts, and I'll explain the other parts too. But the first part of Polya's theorem is that the simple random walk on the integers is recurrent. So this random walk always comes back to where it started. I'm going to try to explain why this is true. So the proof of why this is true is a bit technical. You have to know some fairly advanced math, or you have to know the state-of-the-art math of 1921, which is quite advanced. But I'll try to give some intuition for why it's true, and hopefully it'll tell us something. It turns out that this is related to Zenos paradox. So let me remind you what Zenos paradox is, or one of Zenos paradoxes. Imagine that I have a runner who runs across a field, and at the first tick of the clock, the runner crosses half the field. The second tick, 1/4 of the field, then 1/8, 1/16, 1/32, and so on. Okay, so each time the runner runs a half of what she ran the previous tick of the clock. And it turns out that the runner will never reach the end of the field The way to see that is to notice that the length of the field is 1, and what the runner is doing, they're always having the distance left to run. So if I want to walk across the stage, first tick of the clock, I walk halfway across. The second tick, I walk half of what's left, so I'm not going to reach the end. The third tick, I walk half of what's left now, so again, I'm not going to reach the end, and then half of what's left, and so on. So this is what this runner is doing. They're never going to reach the end. If you sum up all these numbers to infinity, they do reach the end, okay, in some sense. So time infinity, they reach 1, which is just another way of saying they're going to get arbitrarily close to 1 to the end of the field over time. I don't want to get into a philosophical discussion of Zenos Paradox. I want to notice another thing. Imagine a different runner, and this runner is going to go through 1/2 of the field at time 1, then 1/3, then 1/4, then 1/5, and so on. It turns out that this runner will reach the end of the field. In fact, 1/2 plus 1/3 plus 1/4 is already more than 1, so after 3 ticks of the clock, this runner is going to cross to the end of the field. The more interesting thing is that no matter what the length of the field is, imagine that this is counting 1/2 of the length of a football field. So I'm going to do 1/2 the length of a football field at time 1, and then 1/3 a football field at time 2, and so on. The question is, how far am I going to go if I give myself enough time? The answer is there's no limit to how far I'm going to go if this is what I'm doing. So I'm going less and less every time, but somehow still, given enough time, I'll go any distance. Given enough time, I'll cross enough, I'll get to the moon from here. So the sum of all these numbers doesn't have a limit, so right that the sum is infinity. So the runner will reach the end, but in fact, given enough time, she'll go through any distance. So some of these infinite sums of numbers are bounded, are finite. You never cross some line. Other sums, like this one, cross every line eventually, even though the numbers are getting smaller and smaller and smaller. Okay, so what does this have to do with our random walk? Let's try to understand what is the probability of coming back to 0 at a particular time t. So let's remember what happened at time 100. At time 100, I was most likely between -10 and 10. So you can imagine that more or less, the probability of when I am is spread more or less equally over 10 different locations. So in each one, it's going to be more or less 1/10. In fact, the probability of being back at 0 is very close to 1/10. More generally, it turns out that at time t, the probability of being back at returning to where I started is about 1 over the square root of t. So at time 100, the probability back is about 1/10. Time 10,000, it's about 1/100. At time 1,000,000, it's about 1/1,000. What Polya proved is the following. He realized that if you take a sum of these return probabilities, I'm going to sum the probability that I come back at time 1 and the probability that I come back at time 2 and so on. I'm going to sum all these numbers. If this sum is infinite, if there's no bound to this sum, then the random walk is recurrent. Somehow if this sum is infinite, then these numbers are big, so I have a high chance of returning. If these numbers are small, in the sense that their sum is finite, then the random walk is transient. And it turns out that if I sum the return probabilities for this random walk, which is 1/√t, 1/√2 plus 1/√3 plus 1/4, and so on. So this is an exercise that our freshmen will do here. This sum is infinite, which means that the random walk is recurrent. Okay? So let's move it up a notch, and let's go to 2 dimensions. So what I'm going to do here, I didn't prepare a 2-dimensional array of cones, but I'm going to, again, start somewhere on this grid, say here. And then at each tick of the clock, I'm going to draw a card, and depending on which suit it's from, one of the 4 suits, I'm going to move either left or right or forwards or backwards. And then draw another one, and again, move either left or right or forwards or backwards. Now you can ask the same question. Do I eventually come back to where I started? Okay? So somehow there are a lot a lot more places to go here on a line. I'm very constrained to be on a line, so maybe it somehow makes sense that I keep on coming back. But in this two-dimensional grid, I can go this way and that way, and maybe sort of come back, but just miss it and go around it and go in some other direction. It's not clear what happens here. But it turns out that the same sort of reasoning that we saw before can be used to solve this question. And what we have to do, we have to calculate the probability of coming back, then sum them all and see if the sum is finite or infinite. What is it going to look like at time t? So let's look at time 1 million. What is the probability that I'm at each particular point on this grid? It turns out that this time it actually looks like a bell, not just like a slice of a bell, but an actual bell. So it's again a bell curve. And it has width square root t. So it turns out that in this two-dimensional random walk, again, I'm most likely not to have gone distance more than the square root of t of where I started. Now, the number of points within a circle square root t of where I started is the square root of t squared, which is t. So here, the probability to be back at time 1 over t, at time t is 1 over t. So the probability to be back at time 100 is about 1 over 100, instead of 1 over 10 that it was before. It's much lower than it was before. At time 1 million, the probability to be back is 1 over a million. But if I sum all these probabilities, this sum is still infinite, which means that again, I'm going to come back again and again to the origin. This is again a recurrent random walk. So when I have a two-dimensional walker, they're going to return to where they started for sure. With probability 1, they come back to where they started. So what would be the next question that we want to ask? 3 dimensions. So what are we going to do in 3 dimensions? This would be very hard to demonstrate here, but you can imagine a bird. Maybe I should have brought a drone. And the drone is either going to go left or right or forwards or backwards, or it's going to go up or it's going to go down, each with probability 1/6, because I have 6 different options of where to go now. So because I don't have a drone, I have a YouTube video. And this is a simulation on a computer that somebody did. They're sort of zooming out and rotating it as it's developing, so you can see it from all directions. But this is what it looks like. This point is doing exactly what I described. It's moving up, down, left, right, forwards, backwards, each with probability 1/6. And now we can again ask, what is the probability that we come back to where we started? So this time, again, you should ask yourself what your intuition tells you if you've managed to develop one by now, but somehow it seems very easy to miss this point that we started at. There are a lot of different places that I can be in 3 dimensions. I think we probably started somewhere. Okay, I don't know where exactly we started, maybe up here. But so here's what happens in 3 dimensions. It turns out again that I'm not going to go more than the square root of t away from where I started. So the distance that this particle went is again much, much smaller than the amount of time it spent walking. It's doing 1 move in each time period, but because it's not going in a straight line, but going randomly, at time t, it's only going to go square root t away from where it started. So that holds in every dimension. But now there are a lot more places within square root t of where I started. At time 1 million, square root t is 1,000. And at distance 1,000 of where I started, there are about 1 million points. It's going to be the square root of t cubed. And that's the probability of coming back. It's 1 over the square root of t cubed. This, when I sum up these probabilities, this sum turns out to be finite. Okay? So something very interesting happens here. This random walk is transient. It may come back to where it started. Maybe this bird goes up and down, just comes back right away. Maybe it goes up, down, left, right, right, left, down, up, and comes back to where it started. But eventually it's going to go away and not come back again. And this happens in the transition between 2 dimensions and 3 dimensions. Okay? So this random walk is transient, and this is what is usually called Pauli's theorem. It tells you that in dimensions 1 and 2, the random walk is recurrent. In dimensions 3 and actually higher, the random walk is transient. And this has actual implications. For example, some biological processes, when they happen on a membrane, they behave differently than when they happen in 3 dimensions, say in the inside of a cell, because there's this random walk element involved. Okay, let's look at a different random walk. So I'm going to go back to 1 dimension. But this time, I'm not just going to go with probability half and half left and right. I'm going to go left with probability 1/3 and right with probability 2/3. So imagine maybe I'm still pulling out these cards, but I only go left when it's a face card, and I go right with all the other cards. I think that should give me more or less 2/3, 1/3. So I'm much more likely to go right than left. And over time, this will accumulate. So if we look here, this is what happens at time, maybe time 50, time 50 or time 100, but I started at 0. This is my probability of being at each particular location at this time, and you can see that the probability of being back at 0 is already very, very small. I'm most likely to have drifted to the right. Yeah, so this should be at time 50. I've most likely have drifted to the right, and I'm over here. So it's still going to look like a bell curve, but instead of being centered at 0 and giving a lot of probability to being back at 0, it's going to be centered more and more to the right. The center is going to be at about t/3. So at time t, I will more or less have gone t/3 to the right, 1/3. So I'm still not going as fast as if I was just going to the right. I'm only going at 1/3 the speed. But the probability to be back is now very, very small, and this random walk is transient. Again, I might come back. Maybe I'll go to the left and then to the right and left, and right, and come back. But eventually, I'm guaranteed to leave and not come back again. So this is another example of a transient walk in 1 dimension. The simple random walk in 1 dimension keeps on coming back. Okay, so we've looked at 1, 2, and 3 dimensions, and you can do this in 4 and 5 dimensions, whatever that means. And actually, anything above 3 behaves the same way and is transient. So the next thing that people did were try to think about random walks, not in any particular dimension, but in completely different geometries. This is going to be non-Euclidean geometries. So what does that mean? Here's an example. This is called the, well, imagine that now these locations are where I'm allowed to be. And what I'm going to do is I'm going to do a random walk between these locations. I'm going to move along these lines that connect these locations randomly. This picture and this picture actually are of the same geometry. Here you can see it. You can see the symmetry very nice. This geometry, or this graph as they're called, is called the 3 regular tree. Tree because I guess if you look at it like this, it actually looks like a tree. 3 regular because each location, each point is connected to exactly 3 other points. And one important feature of this graph, which differentiates it from the grids we've seen so far, the 2-dimensional and 3-dimensional grids, is that there are no loops. If I go somewhere, the only way I can return to where I started is through the same path. I can't go this way and come back through another path. When I do a random walk on the 2-dimensional grid, I can leave a point one way and come back from a very different direction. Here, if I leave this point and go up, if I ever come back, I have to come back from this location. I cannot, this is not connected to this, so I can't loop around. Here's the 4 regular tree. So now it's exactly the same, except each location has 4 different neighboring locations. And again, there are no loops. And you can draw many, many sorts of graphs like this. So this is just a taste of the possible geometries or graphs where you can do random walks. There's a whole universe of these things, and it's very, very interesting to study different properties of these things. So let's be a bit more concrete what I mean by a random walk here. So this is, again, the 3 regular tree. Imagine that there's another line coming out here connected to more vertices. So I'm going to start from one of them, say the origin is here. And at each tick of the clock, I'm going to move with probability 1/3 to each one of the 3 neighboring locations. Okay, I'm going to do this again and again and again. And let's ask the same question. Do I keep on coming back to where I started, or do I leave and never come back? And it turns out that this random walk is transient, so it leaves and never comes back. It's not a recurrent random walk that comes back again and again and again. And the way to see this is to connect it to this random walk with a drift that I talked about before. So before I was walking on the integers, going left with probability 1/3 and right with probability 2/3, and we saw that that was transient. Eventually I don't go, and I leave and don't come back. What's going on here is that when I'm at a given point, let's divide this into levels. So everything that's on the same line is going to be in the same level. What happens when I'm at a certain level, I have probability 1/3 of going here, probability 1/3 of going here, probability 1/3 of going here. So I have probability 2/3 of going up and 1/3 of going down. So if we only look at what happens to my height, it's exactly like this random walk on the integers with a drift. It has an upward drift. So my height is going to eventually not go back to being 0, so I won't come back to this point where I started. So this is a transient random walk. And you can see it here also. If I start from here, you could, if I say go up, I have probability 3/4 of going further away from where I started, and only probability 1/4 of coming back. So again, I'm going to tend to drift away, and eventually I won't come back. So here's another question that people have asked. Does the random walk return to all directions? So now I want to know not whether the random walk returns to where it started, but does it return to all directions? So what do I mean by that? Imagine that we have this random boy doing the random walk. Imagine in 2 dimensions, so there's this 2-dimensional grid, and I just stand where he started, and I let him do his walk, but my hand points to where he is. So maybe he starts over there and then goes there, and my hand points to where he is. And the question is, am I going to point in all directions again and again and again? Or am I eventually going to sort of fixate and not change the direction? Will I eventually not go back to pointing there? And in 2 dimensions, the answer is very simple. I'm going to point in all directions again and again because the random walk is recurrent. So the walker comes back to where I started and goes off. And each time they're going to go off in a different direction. So I'm going to point in all directions again and again and again. The more interesting question is what happens in 3 dimensions. In 3 dimensions, the random walk is transient. Eventually, it leaves and never comes back. So this drone or bird that's doing the random walk, maybe it'll come back, but eventually it won't come back. It'll be very, very far and stay very, very far. It'll go further and further out. So when my hand is pointing at where it is, it's going to be a very small speck in the sky that's still only moving 1 step left, right, up, or down. So my hand is only going to move very, very little. And now it's not clear whether it's going to go again and again and again to all directions. So it turns out that this was solved, and there's a theorem called the Denis Theorem. And it turns out that in any dimension, the random walk will visit all dimensions again and again. So even though this random walk becomes, in 3 dimensions, becomes very, very far, if I'm pointing there, over time, if I give it enough time, I'll end up pointing there, in any possible direction, again and again and again. And I'm going to call random walks that have this property directionally recurrent. So the direction is recurrent. They come back to all directions again and again and again. And the Denis Theorem, it's named after 2 French gentlemen, says that in any dimension, the random walk is directionally recurrent. It'll visit all directions again and again. So let me tell you a little bit about the history of the Denis Theorem. And for that, I have to tell you about David Blackwell. So David Blackwell was born in Illinois in 1919. He went to Urbana-Champaign. He was sort of a child prodigy. He went there when he was 16 or 17. He graduated at 19. He got a PhD at 22 in math. He later did research in maths, statistics, economics. He was very prolific and had a lot of great contributions to many fields. And his first job after the PhD was a postdoctoral fellow at the Institute for Advanced Study at Princeton. So the Institute for Advanced Study was already there, a very prestigious place. They had Einstein there as one of the founding members, and von Neumann, who was an important mathematician, and Blackwell actually had a chance to talk to von Neumann and work with him. It's in the town of Princeton, and it's not part of the university, but they have a lot of joint, collaboration. And people from the Institute for Advanced Study often went to take courses in Princeton. The institute didn't have its own courses. Now, David Blackwell, unlike other people in his position, was not allowed to go to Princeton to take courses, which is why he left. And the reason he wasn't allowed to do that is because he was black. So in Princeton in 41, there were no black students. The first undergrads graduated later. Okay, during the 18th century, there was one or two after the Civil War. The first PhD graduates from Princeton who were African American, it's only in the late 50s. So Blackwell left. He got a position at Howard University, which is this historical black university. He was there for 12 years. He applied to Berkeley when he went to Howard, but again, he was denied due to racial concerns, so they weren't really trying to hide it. They thought his work was good enough. But in 59, he was given a position in UC Berkeley. He was the first tenured African American there. And in 65, he was the first African American in the American Academy of Sciences. So somehow, to some extent at least, he was accepted eventually, but it was a long and arduous road. Despite all this, he has great contributions across many fields. Every economist knows his name, as well as people in probability and other fields of math and statistics. So it turns out that Blackwell proved the Choquet-Denis theorem a few years before Choquet and Denis. But still the name Choquet-Denis theorem is how this goes, but maybe it should be called Blackwell's theorem, and it's the same theorem, just a few years earlier, that these random walks are directionally recurrent. So this term directionally recurrent is a term I made up, so I apologize to any experts in the audience who are wondering what I'm talking about. So what happens to a random walk on this regular tree? Well, remember that it's transient. Eventually, it leaves the point where it started and never comes back. Let's look at it here, or maybe here. I start here, and eventually I leave and don't come back. Imagine that I leave and go up the last time that I leave and don't come back. Well, if I left going up and I never come back to this point, I have to spend the rest of the random walk somewhere up here. I can never go to this branch of the tree because I left this point and I'm not coming back. If I was going to get to this branch, because there are no loops, I can't loop around and come to this branch. So once I've left, I'm stuck in this branch forever. So I might leave and come back and leave and come back, but eventually I leave and don't come back. So if you have a person standing here in the middle and pointing at the random walker, they're not going to point in all directions again and again and again. Eventually they're going to point, say, upwards, or maybe this way, or maybe that way, each with probability 1/3. So there's a random direction that this random walk converges to. But actually the direction does get fixated from some point on and doesn't change. So this random walk is not directionally recurrent, it's directionally transient. And there's a big question, which is, for which kind of geometries or which kind of graphs like this, I've only shown you these very few examples, is the random walk directionally recurrent? If I show you a picture like that of a geometry, can you tell me what the random walk will do there? And this is a difficult problem. We've made some progress on this, so this is together with two Caltech grad students who are extremely bright, and another collaborator of ours, Yair Hartman, who's at Ben-Gurion University in Israel. And we've understood this for a certain class of geometries in some sense. I don't want to get into the technical details, that are called groups. So some of these graphs that come from something called groups, whatever that means, we now understand better this question for them. So this is some recent progress that's been made. So the last thing I want to tell you is about a connection to economics. It's a bit of a tenuous connection, but I'll tell you anyway. So here's a little riddle. Imagine that I have a person standing at each node here. I also have a person standing at each node here. And they have to agree on a money exchanging scheme. Each one of them has to choose one of the people who's next to them. So in this case, one of the 3 people who are next to me. In this case, one of the 4 people who are next to me. And give them $1. The question is, can we do this in such a way that everybody becomes richer by $1? So I give $1, but I get $2. And that's true for everyone. Right, so this sounds very paradoxical. How is it possible that everybody takes $1 out of their pocket, gives it to somebody, and suddenly everybody is $1 richer than they were before? So this turns out to be impossible to do here. There's absolutely no way to do this. It's a nice little argument for why that's true. But here it is possible. So how can I do this here? How do we decide who gives money to whom so that everybody becomes $1 richer? Right, so what we're going to do is we're going to give the dollar down. Each person has 2 people above them and 1 person below them. And each person is just going to give the dollar to the person below them and get $2 from the person above them. Okay? It's called a Ponzi scheme. But it actually works here because this graph doesn't end. So there isn't the layer of fools in the end who are left without their dollar. But here, there's no way to do a Ponzi scheme like this. So there's something really different about this geometry and this geometry. Even though here we also have infinitely many people, there are no Ponzi schemes here. Here there are Ponzi schemes. And this turns out to be related to this question of directional recurrence of the random walks. So this is related to a lot of work done by Furstenberg, who was born in 1935 in Berlin. They fled Germany in 1939 to the US. He studied at Princeton. Then he was a professor in the University of Minnesota, and eventually he moved to the Hebrew University in Jerusalem. He also happens to be the academic advisor of my advisor. And what he showed, I guess this is also related to results by other people, is that graphs in which wealth creation, in which these Ponzi schemes can exist, are directionally transient. So when I have a graph like this one, imagine that here we have this point in the center, and everybody just sends $1 towards the center. So this person is going to send $1 here, and this person will send $1 here, this person will send $1 here, and so on. So here everybody becomes $3 or $2 richer. So graphs like this, where you have these Ponzi schemes, the random walks on them are directionally transient. They don't come back to all directions again and again. Okay, so there is this mathematical connection between these 2 seemingly unrelated questions. Okay, thank you very much.